Hi friends, very good morning and good evening. So in the last video we discussed about how to create a data pipeline, where we discussed how to create a PyTorch dataset and data load, right? The next important step in deep learning is what do we pass this data to, and it's a deep learning model, right, or a function, the way we looked at it in one of our earlier sessions. So in this video we will understand the different CNN architectures at a very high level, good enough for us to play with most of the image classification problems. Okay, by the end of this video you will understand what we will look in this video and what we will look in some other video. Probably it can come as a video or it can come as a blog from our end. So in this video we're going to cover this get model function. What is happening in the get model function? We'll almost build it from scratch as usual. So before building this get model function, let's go and take a look at different architectures. Okay, so the get model function here actually returns you an efficient model, right? But efficient does not come along with torch vision models. So you have to install efficient library. Let's also see what is actually happening in this Melonama efficient model, and let's just copy and put it there for us to easily look at what is happening. It is all in the helper classes, which you can see it in the Kaggle kernel link which was shared with you, right? So before getting into this efficient, okay, PyTorch comes with Torch Vision package. It's a separate package, but most of us would end up installing when you end up installing PyTorch. Okay, so that comes with a lot of pre-trained models and a lot of model architectures. So I've already imported that, and you can see that there are a bunch of architectures, very important architectures. It's actually, there are a huge number of architectures, right? So let's look at a couple of them. The first one we will look at is resnet 34. So if you see this architecture, you can see that it has a bunch of convolution, batch norm, ReLU, max pool, bunch of layers that does some kind of operation. Okay, and again another set of operations, and at the end, right, the most important thing is the fully connected layer. Okay, this is the linear layer which we discussed. So what it does is it takes the output from this entire convolution block, basically the last layer of that convolution block, and passes it through our linear layer, which is wx plus b, right? And it maps to 1000 categories. Why 1000 categories? Because by default most of the architectures are trained on ImageNet, and ImageNet has got 1000 categories, different categories, right? So let's look at different architectures before we go into efficient. Let's look at Densenet. So Densenet also has something pretty similar to that architecture. You have a lot of convolution layer, and there are like things like skip connections and all, which probably we can have it in a different video. We'll explain what is a resnet architecture, how can you build a Densenet by making a small extension to that. We'll look at it in a different video, but in this video what we are really focused is how does different architectures look like, and what is one parameter that mostly you have to change to make it work for your classification problem. Okay, for Densenet also you can see that there is a final layer called Classifier. The different names, right? Here it's called fully connected, FC short form, and then here it's called Classifier. Okay, thanks to grammar it's explaining us a couple of things. And then for efficient, if you see, the definitions are much more complex than any of these things. These are modern neural network architectures, and I believe efficient is not a hand designed architecture. It is more of a computer picking up different layers and figuring out how to make efficient architectures. Okay, and there are different architecture sizes starting from B0 to B7. Most of these models have different architectures. Let's look at how many ResNet variants are there, right? If you look at ResNet, right, it has from 18 till 152, and most of them have the same architecture, right? Let's look at ResNet 18, right? It also takes input of channels 3 and it outputs the 64, the first layer, and the last layer as usual it takes 5, 12 and 1000. Okay, but one thing changes is this input features for different architectures. Let's say, for example, let's take the biggest architecture and say what happens. there will be a lot of changes to the architecture, but the one thing which we really worry about is, for at least for most of the classification problems, is what is this input feature layer, right? So this is how most of the architectures look like. For efficient net, you will not have it in PyTorch Torch Vision library. You have to install it from a third party. There are a great number of people, not great number of people, few people who have volunteered to create a repository, amazing repositories for efficient net. What we will do is we can just quickly install one of them. In my case, it's already installed. Let me just show you how to just save it. Okay, and the one which I'm using is, I think this is one I'm using. Okay, pip install efficientnet PyTorch. And how do you create a model with that? You say efficientnet.from pre-trained. Why it's pre-trained? Okay, when we talk about pre-trained, means okay, we'll just get back to the resnet architecture and I'll show you how to download the pre-trained weights in a moment. Okay, if you want the pre-trained architecture, basically you don't want random weights, but you want weights that can identify one of the 1,000 categories, and you say from pre-trained, and you tell that you want a B0 model or till B7. Okay, and the complexity, basically the computational capacity, increases from model 0 to 7. Okay, so now we looked at what high-level architecture contains of. Okay, now what I'm going to do is let's create an architecture. Let's create a model which lets us pick any of the resnets that are available in Torch Vision library and map it to one category. How do we do that? I'm going to do it from scratch, so there can be some mistakes, so please bear it with me. Let's say Melonama, call it resnet. Okay, and every neural network architecture in PyTorch should be a subclass of NL.module. Okay, and we need some init. We want to initialize a couple of things. So let's have our init function, and then say, and the most important thing which I end up, I don't think it's this way, I think it is super, and then say init. Okay, and this, let's just quickly look at, yeah, okay, I'm right. I always end up getting confused with this one. Okay, all it does is any parameters that you pass to this particular class, it just pass to the parent class. Okay, and then we need a backbone, right? So let's say backbone equal to some model, right? So what would be the model? Let's say we want, okay, we have imported it as models, right? So you want to say models dot resnet 34. Okay, and say pre-trained. Okay, this is what I was talking about. If you want a pre-trained model network, all you need to say is pre-trained equal to true. Okay, now what we're going to do is, there are a couple of different ways you can do. Okay, let's say you want to calculate the input features. One is we can hard code it, because we know that resnet 34 has 512. We can hard code it, or the other ways we can create it dynamically so that we can change the model whenever we want. Okay, what are we gonna do it in input features? We'll say backbone.fc. Okay, the one good advantage of working in a Jupyter notebook is you can explore it in real time. So it's a good practice to always believe that you could be doing something wrong, and which is very common in programming, right? Backbone dot, let's say I'm assuming that it has got an attribute called fc. Okay, in this I want the in features, right? Let's say dot in features. Okay, and I'm assuming that it would work, right? So we store it as in features. Okay, there's one more thing that we need to do. We want to remove the last layer. Okay, there are two ways to do it. One, either we can change the input features as it is, or we can remove it so that we can do a couple of more tweaks to it. Okay, let's look at what are they. Okay, how do we remove it? So backbone is this entire resnet model, right? So you want only the model till here, right? Some of the models will have something like feature extractor or classifier or something, but I don't think resnet implementation has that. So when you don't have that, the other easier way to do is call the children functionality, which returns a generator, but we need to look at it, right? So let's convert into a list of all the layers. So it's a Python list with all the functions or the PyTorch layers in it. Okay, now we can do anything that we do with Python list. Okay, now let's say we don't want the last two layers, right? Let's remove this. Okay, so we get till here, and now I want to make it again a deep learning architecture or PyTorch model. Okay, so I have to say nn.sequential, and it takes layers. Okay, it's take a different layers as an argument, different functions as an argument, not a list as an argument. So let's print this and see if we get a neural architecture. Yes, we have a neural architecture, and this can become our actual backbone. Okay, so I'm using something which I have not explained to you. Let me explain to you. So here I purposely did not say self dot. Why? The moment we say self dot, it gets registered in PyTorch architecture. Okay, which you don't want. If you do that, then the gradients calculation gets kind of corrupted, because you want the gradients to be calculated only for this backbone and not here. Okay, so be careful. It's something which we can forget it if you're starting completely new with PyTorch. So be careful when you initialize the backbone. Okay, so then now we have network architecture only till here, right? So we want a classifier. So what is a classifier? The classifier can be anything starting from a simple linear layer. Okay, so here this is where we need the in features. Okay, and we need the output, so we can say in out. Okay, and now what we can do is to make this architecture more dynamic in nature, because right now this architecture always gives a resnet 34, which I really don't want it to be. We can say let's call it backbone architecture, and let's call number of output that I want. Okay, I know it's 1 in this case because we're just predicting if it's malignant or not. Okay, and in this, let's say models, that is if we don't pass anything to it, then just give me a resnet 34 model. Okay, give me a pre-trained model, because most of the time there is a very high chance, 99% probability that you want to use a pre-trained model. You're using it in a completely different domain which is not related to ImageNet look feel data. Okay, any data that looks like ImageNet, but that's what I meant. Okay, so we have a self.classifier now that actually connects the data from backbone. There is still something that we have to do. So here all we are doing in the initialization is we're telling that we need these layers, but still PyTorch doesn't know how it's going to connect it. Okay, now we have another important function in nn.module, which is forward function. Okay, which takes in self and some input. Okay, most of the time we can call it as x. Basically that's the input that is being passed to the model. Whatever data we created in the previous step data pipeline, that is being passed into the model, and when we pass it to the model, it actually gets passed into the forward functionality. So here what you want to do is, let's call x and let's pass it to the backbone that we created earlier. Okay, so what would happen is our input is passed till here, till the last average layer. What does it return? It should return something like 512 comma something like 7 comma 7, depending on the shape of the image that you pass it to, right? But when you develop it, you may not know that information. Since I have already worked on it, I know that thing. So how do we quickly check it? Let's take a batch of data, right? I just pulled a batch of data from train.dl. It's taking time. Thanks, it worked. And then let's say, okay, here we created our model, right? Let's call it backbone equal to this. Okay, and let's say backbone of XP, and I want to know what is the shape of it. That's what I'm more interested in. I'm not passed. Okay, thank God it worked. Okay, because I'm not passed it to GPU. Sometimes if the images are larger, it can take quite some time. But this is still a smaller image size, so it has done faster. So you get something of 8,8. Okay, that is for images of shape 256, 256. When you have something bigger, then this changes. Let's also try to look at it, right? Let's create a random tensor. Let's say of batch size 2. I'm running it on the CPU. I've not pushed it to GPU, so I don't want to create a larger one. Let's say 128, 128. Okay, let's call it our input tensor, which is the new batch, random batch that we have created. Okay, and now let's pass this and see what happens. Okay, see, you can see that this thing changes. Basically, this is what your convolution layers, your receptive field. This is related to receptive. Basically, you have 512 filters of each size 4,4. We did not explain convolution, so if you're completely new to what is a convolution, you may not find it very clear. It's absolutely fine. I'll try to give you a few links. Convolution layers have been there for quite some time, and there have been amazing explanations. I'll try to put in the description some of my favorites. If you still find some part of it difficult to understand, please leave it in the comments. I'll try to explain it in a different way. Okay, so we can see that the input size changes, the output of the backbone also changes. Okay, so now, so if you look at it, it's a 3-dimensional tensor. We want a 2-dimensional tensor to work for linear layer, right? So what we do is, first thing is we apply some kind of pooling layer on this. One is to reduce dimensionality and to the context that we can gain. Okay, so to do that, what we can do is we have different layers that we can apply. One is average pooling. Okay, average pooling 2D. The problem with this is this works only for a specific size. So most of the model neural networks don't use average pool. Instead of this, they use this particular one. Okay, let's see what this does by passing this as an input. Okay, and then saying that how many filters you want, what is the output that you're looking at. Let's, as usual, print the shape. You don't want to look at the tensor because it's a bunch of numbers which we human brains are not designed to understand in general, right? So all we are doing is you have a matrix of 4 numbers and 512 matrix of such nature. You're just taking an average of each 4 boxes, right? That's all we are doing here. Now still it is not in the way we want it, right? Because we want a 2-dimensional tensor. So what you can do is you can just flatten it. Now, what is flatten it? You just make it 512, 1. So there is a function called torch.flatten, and we can say, I think it's 1. Let's just quickly look at the shape. I don't remember the dimensions. I think we are good to go. Okay, this is what we exactly want: 2, 512, not 2, 512, 1. We just need 2, 512. Okay, now we have the exact tensor that is required to be passed to the linear layer. So what we will do is we will build the network architecture. We will say x equal to f dot adaptive average pooling 2D and pass the x and just say that you want output as 1. Okay, then let's say x is equal to torch dot flatten. Okay, pass x and say 1, and then you can say x is equal to self dot classifier of x. Okay, and then we can just return the x. Okay, x is going to be the output. Sometimes these are called x, or sometimes you can call them as out. It's all up to you and the naming conventions that you want to follow. Okay, so I think our required architecture is ready. We can do some customizations. So for example, you don't always want to use an adaptive average pool. So one common convention is to pass the output of this to something like, let's call this x average. As I told you, there are different ways you can do this. There's another way called x max pooling. So it's not x max pooling, you actually apply adaptive max pooling. Instead of taking an average, what you do is you apply a maximum of it. Given 4 numbers, what is the maximum of it? Okay, and then we can concatenate these two using torch.cat, and then you can flatten that here. That's kind of improves the results slightly, but I leave that to you. You can try an experiment. And the other things that you can try and experiment is, instead of saying nn dot linear here, you can say nn dot sequential. So basically, instead of having a simple linear layer, now you can have a small architecture. Let's say in feature. Okay, let me remove this thing. Okay, in feature by 2, and we may want to pass it through a batch normalization layer. Batch normalization layer is responsible for keeping things stable. What it does, it actually does something very interesting, which we'll probably look at in another video. Then you can have a dropout layer. Okay, and then you can say dropout of 0.5. What is a dropout? Again, dropout is a very interesting layer. Okay, I think dropout is something which we can explain very quickly. Given a vector, let's say of 100 numbers, right? If you say probability of 0.5, randomly with 50% probability, it can make these numbers as 0. Okay, why do we use it? We want to prevent our model from memorizing the training data set. We don't want the model to remember all the training examples that we have provided. What we really want to do is, we want the model to recognize the features that can be used to identify to do a specific task. In our case, the task is identifying melodrama, right? We can do a lot of fancy things in this classifier, but let's keep it simple now, and just let's say I want n underscore out. Okay, so we've written a model, and it's always a good practice to see if we are getting the correct outputs. Our model is melodrama resnet, and we don't need to pass anything. Okay, I mean, we can pass if you want, but let's look at both the examples of passing something and not passing something. Okay, something went wrong. What is that went wrong? Okay, that's not what I expected. Let's see what happened. Okay, so we did not remove the max pooling, the change that we did for max pooling. So the input of this is directly passed to the flatten layer, which is not what we wanted. So this is where quickly checking it actually helps. It is much easier to debug your code when it is small and when you're iteratively developing it. So 64 stands for our batch size, and this is 1. Sometimes to change it, to use it in a loss function, we may have to apply the squeeze method. So basically, squeeze, what it does is, let's say it removes the dimension 1, and you have basically a list of 64. Why do you want to do that? Because I'm not sure if you have done that in YB. Okay, here we have already unsqueezed it, so we don't want to apply squeeze, but sometimes you don't do it there, then you end up doing it here. It's a matter of choice where you want to do it. Okay, so this is what is happening in a model, and we built our entire PyTorch model from scratch. So a lot of things that actually changes is this architecture resnet 34. Okay, so now we have created this. Let's say you want to quickly try. You want to go a bit crazy and say, no, let's not go crazy because we are running it on still on CPU. So let's go a bit humble, and let's say resnet 18. Okay, and you want prepaint to be true. Okay, it's downloading since I've not used resnet 18 in this machine. This is the first time I'm using it. It's downloading. Now let's see if things work. I hope it works. It should work, right? Yes. So now all you need to do is just change the model to whichever model you want, and the model is ready. And when you do it this way, you can have flexibility to a lot of experimentation. So since we said that, okay, there are multiple ways of doing this adaptive average pooling. Basically, they call it concat pooling, or there's something called gem pooling. There are different ways you can do this particular part. So what we can do is we can make this also as a function, and I think I would have done that in the kernel. Okay, if you see here, okay, pool type. Okay, and that's what we will be applying here. So this is pretty similar to what we have built here. Okay, just that we built on ResNet architecture, which is part of Torch Vision library, and in the kernels for EfficientNet. Okay, ResNets are also pretty good, and let me show you another important secret. Not a secret, but it's a very important thing which a lot of people may miss it. The default weights are trained on ImageNet dataset, right? But when you go to PyTorch Hub is again another place where you have a lot of different models. Okay, you have this amazing repository called semi-supervised and semi-weakly supervised ImageNet models. There is a very high chance that you may want to try this in your real life problems or in the Kaggle competitions. Okay, so why it's important is, if you see the ResNet 50, okay, semi-weakly supervised, this top one accuracy is 81.2. okay, while as ResNet 51, ResNet 50, the actual ImageNet would be way less than that. Okay, browse state of art. I think we should be able to pull this. This is a good place to explore. Okay, it has got a lot of papers getting published, and there are also benchmarks to it. Okay, let's look at ResNet 50. Okay, I'm not sure if it's there. Okay, but I think we should be able to find it here. Let's search for ResNet 50. 50. Okay, I don't think they have it because it's a very old model. Okay, but as you can see, if we can just sort it based on accuracy. Okay, I think it's already sorted. Okay, and SSL should be around. Okay, let's look at EfficientNet, right? EfficientNet is considered to be, well, EfficientNet B8 is at 85.4 and EfficientNet B7 is at 85% of top one accuracy, right? Which one was that? EfficientNet B8, right? If you look at this, you almost get a similar level of accuracy at next 101, and 81.2 is not a provide, and it's ResNet 50 and ResNet 50 32 into 40 are way faster than EfficientNet, particularly on NVIDIA GPUs most of the time, unless until it's fine-tuned. Why? Because ResNets have been there for several years now, and the NVIDIA company has been optimizing their GPUs for that. So EfficientNet also would be becoming faster over a period of time on NVIDIA architectures. Right. So okay, let's come back to this topic. So instead of using the Torch Vision weights, you can use these weights. And how do you do that? Instead of using Torch Vision library, all you can say is, you can just say model is equal to this. Okay, and let's just do it. And just you call this and you get a model ready. Okay, since I've already used it, it did not download, otherwise it'll download a bunch of weights. The architecture is pretty similar. I think it's almost similar actually in the Torch Vision models. Yeah, okay. So let's take a look at our get model and let's see if we have missed something. I think where is our get model? It's here. Okay, so there are a couple of things we do apart from getting the model and the get model function, right? One is we check if the machine on which we are running this code has got a GPU or not. Okay, if it has got a GPU, then we try to put the model into the GPU, right? Run things faster. Running things on CPU is not faster in most of the cases. So how do you put a model or a tensor in a GPU? It's very simple. Every PyTorch module or tensor has this to function, pass it. Pass to it a parameter called device, which actually says torch.CUDA device, whether it's CUDA or CPU. So let's look at this function since I have not showed you that. Let's search for it. Okay, this is all it does. Okay, so if basically GPU is available, then we say torch.device of CUDA. If it's not, then we say torch.device of CPU. Okay, so let's get back to our thing and let's see what we have missed. So we are creating EfficientNet model. Here also you have to just change the name of the model and we get the architecture. We can have one which is clubbed both efficientnet and resnet. The only reason, slight reason, is this has got this underscore fc and there it is fc. Probably we can take a look at what is the name of the model and you can do it, but how much complex you want to do, it's up to you. Okay, and this is something which is kind of important in some of the problems. You can experiment even in this problem. So what is this? What does freeze backbone means? Right, and there are a lot of complexities in it which we will be exploring in the coming videos and separate videos itself. So when we say resnet 152, right, we get this entire architecture. So this entire part we store it as a backbone, right, and it's a common practice to keep this as frozen. What does it mean? There is no learning that happens, and that's what is transfer learning, right? We spoke about pre-trained weights in one of our previous videos. Sometimes when you have very less data, let's say you have 100 or 1000 examples, you don't want the model completely to be learning, because there is a very high chance it can overfit, right? So in those scenarios, what you want to do is you want to completely freeze this. That means this model, given the same input, it always gives the same output. Okay, and there is no feedback that passes through. When you actually try to learn, there's nothing happens, right? So what you actually say, how you do that is you just say requires grad. Basically that's required gradient. In simple English words, it's a feedback. It's oversimplification, but let's get to it. When we understand what are gradients, how do we backpropagate it, we'll understand more about it. And there's another thing called optimizer. Okay, you would have heard about STD, ADAM, different optimizers. We have to pass these model parameters. The parameters are nothing but the weights and biases to the optimizer. That's what we do. And then we have something called learning rate, weight decay, which we will discuss about it when we actually cover the optimizer in one of our future videos. And that's all is happening in get model. Now we know how to create our data pipeline, and we know how to create a model. We know how to create a model that can take any efficientnet name and give a efficientnet architecture for our particular classification problem. The same thing with resnet architecture, we built it from scratch. And the last button, we have the generate predictions. That's another key thing which we'll look later. The last one that we're going to look is the fit function. A lot of key important things are there in the fit function. Again, there are certain components which we will look at it from a higher level, and we will dig into these components or try to even build from scratch in one of our future videos. Thank you guys for watching this video. If you like the video, please hit the like button and subscribe. And if you have any suggestions or any comments, please leave in the comment area. Thank you guys.